Oh, so okay. So topics covered in chemistry. These are topics we're going to be covering in chemistry. I think we're going to go up to maybe topic 3, and then I'll let you guys off for lunch. I also want lunch as well. Right. First topic is atoms and periodic table. This one is a relatively easy one. It's very straightforward. With the mass and isotopes topic, you need to know the definitions by heart. So you need to know all of these definitions. You just need to know them, and you need to know them word for word. The atomic number. So usually you're given like a number on the periodic table, like for example, Na, and you're getting a number on top and on the bottom. The bottom number is the atomic number, and that's the number of protons in an atom. If it's just a basic element, the number of protons are going to be the same as the number of electrons. So you can think about the atomic number being the number of protons and also the number of electrons. The mass number is the sum of protons and neutrons in the nucleus of an atom. So it's going to be the top number you see usually when you have the element, the top number. And that's the total number of neutrons, the total number of protons. Isotopes, they are the isotopes of an element of an atom, basically. They have a different number of neutrons, but the same number of protons. So I could have sodium isotopes where they have the same atomic number and a different mass number because they have different number of neutrons, but the same number of protons. So it could be sodium, like, I don't remember which sodium is 12. I don't know. Let's say it's 12. They're both 12 atomic number, and it could be like 30 mass number and 31 mass number. These are isotopes. Same element, same number of protons, different number of neutrons. So same atomic number, different mass number. Relative atomic mass, AR. This one, I cannot emphasize this enough. They ask this maybe once every year, once every 2 years in the exam for the definition. I don't know if it's your year, but it's important to note. The relative atomic mass definition, word for word memorized, is the element is the weighted average mass of all the isotopes of an element compared to 1/12 of the mass of a carbon-12 atom. That is, I cannot expand more than you just need to memorize the definition of it. You also have to be able to calculate the relative atomic mass through different isotopes. You have the equation right there. It's the sum of the mass of each isotopes times the abundance divided by 100. So if there's like 60% of 30 and 40% of 28, you're going to do 60 times, I already forget the numbers, but 60 times 30 plus 40 times 30 divided by 100. I don't remember the numbers I gave, but that is the equation you need to use. Ions are particles with an electric charge. So they don't have the same numbers of protons and electrons. So remember when I said elements with atomic number, they have the same number of protons and electrons. In ions, this is not the case. In positive ions, or some people like to say cations, they have more protons than electrons. And negative ions is the opposite. They have more electrons than protons. And they do this, they form these ions by gaining or losing electrons. So positive ions, they're going to be losing an electron. They'll lose an electron, making them positive because electrons itself are negative. So with losing an electron, they're going to become positive. Negative ions, they're gaining an electron. That makes them more negative. So negative ions, cations and anions. The way I memorize it with positive ions, cations are positive, like cat's paw, positive. That's the best way I can explain it and the best way I memorized it. That's how my teacher taught me. Cations are positive, anions are negative. This is all pretty just general content, straightforward content. I'm hoping that was clear. Okay, now here's a question. I'm going to give you guys about 2 to 3 minutes. I'm going to give you guys like maybe 2 minutes to do this question. They should all this. So there's a bunch of math and as well and just definitions. So just have a look at it, have a go at it. Okay, let's have a look at this question. First thing, it's asking you to define the meaning of isotopes. That one should just be the same number of protons, different number of neutrons. That one is already it's a straightforward 2 marks. You're just defining the term. Second question, I'm hoping everyone did do this question, but it's just the math. So using the equation, it's just 69 times 60 plus 71 times 40 divided by 100. And that should give you the answer. And remember, it says give your answer to 1 decimal place. So be very, very careful with that. The answer you should have gone should be 69.8. The third question, give the number of electrons and neutrons in an atom of the isotope gallium 69 and 31. So this is what I meant with the number on top and number on the bottom. Bond number is atomic number. Top number is mass number. It's asking you for the number of electrons. We already know that atomic number is the number of protons. And I've also said the number of protons are the same with the number of electrons when it's just the atom itself. So the number of electrons is simply 31. Now we need to figure out the number of neutrons. We have 69 as a mass number, and 69 is the number of protons and neutrons. We know that the number of protons is 31. So to figure out the number of neutrons, we simply just do 69 times 31, which should give you 38. That's the number of neutrons. To figure out the most likely formula of gallium, the way that I do this is kind of a little bit cheat trick, but I think it works and it really is helpful. It's by looking at the periodic table and looking at the column that is in, what group it's in. If it's group 1, the ion it's going to form is going to be +1. Group 2, +2. Group 3, +3. 4, we don't really look at really. Group 5, -3. Group 6, -2. Group 7, -1. So gallium, if you look at the periodic table, is in group 3. So I instantly say, okay, that likely formula for the gallium ion is probably going to be gallium 3+. That is the trick that I use. I think it's a really good cheat trick and it's really easy if they ask you for an ion. Just look at the group, and the group that it's in is going to be the most likely ion it's going to form. So here are the answers for this question. Should be pretty straightforward, but let me just see. When drawing ions, can you just draw the outer shell? No. I don't think so. I think you have to draw all of them. I think you do have to draw all of the circles and all of the electrons with, I believe that has to be, I think you do have to draw every single shell. Better to be safe than sorry anyway. But I do think you do have to draw all of them. Yeah. Okay. Bonding and structure. Okay, this is such a massive one. It's just very, very content heavy, and I will go through this as best as I can with you. First part, let's just talk about is, oh my God. The first part I'm going to talk about is the ionic structures. Ionic structures are generally giant lattices, and the bonding for ionic bonding is between a metal and a non-metal. So the metal usually is from group 1, 2, or 3, or it can be a transition metal, and the non-metal is from group 6 or 7 likely. With the electrons, how they are bonded together is that they are losing and gaining electrons. So there's going to be positive and negative ions. So the metal is going to lose an electron because that forms the positive ion, and that electron is going to be given to the non-metal. So it's just transferring electrons from the positive to the negative, and that's how they bond together. The arrangement, again, as I've said, is basically a lattice, and it has a very, very high melting point because of the many, many ionic bonds. And the exam boards really like this word, electrostatic attractions. The high melting point is because they have very strong electrostatic attractions due to the ionic bonding. For electric conductivity, it doesn't conduct electricity generally when it's solid. However, if you melt it or dissolve it in water, these ions are going to be positive to move. And anything that has an electric charge can conduct electricity. So if it's molten or it's in aqueous solution, these ions are going to be free to move. They're no longer going to be in this lattice structure like fixed. They're going to be moving around the structure, and therefore they can conduct electricity. So be very careful with this. They cannot conduct electricity when they're solid, but they can when they're molten or dissolved in water. That's ionic bonding. Covalent, generally, there are 2 types. The most common one and the one that usually you will see is the simple molecular structure. That's the covalent, so simple structure. There are giant covalent structures, and the reason I have to emphasize that is just because there are specific giant structures that you need to know. But generally, covalent bonding and covalent structures are simple molecular. The bonding between covalent structures are between two nonmetals. So between two elements, usually from group 6 or 7. Electrons, rather than being transferred, are shared. So they share an electron pair to form that covalent bond. And because they're sharing electrons, there's no ions formed. They're just sharing these electrons. There's no transferring, there's no losing or gaining any electrons. So they don't have any ions. Okay, here's where I talk about the structures you need to know. There's diamond and there's graphite. Graphite we'll look at later because graphite, again, shows up almost in every single exam and it's always a 6 marker. So you need to know it well. But we're going to talk about diamond first. Diamonds are arranged, 1 carbon bonded to 4 others, and they form a tetrahedron, meaning just bonded to 4 things. That's what tetrahedron means. Diamond and graphite both have extremely, extremely high melting points because they have a lot of covalent bonds. But that's only because they are giant covalent structures. Simple covalent structures have very low melting points. Very, very low melting points. That's very important to note. Diamond doesn't conduct any electricity as all electrons are in the bonds. Same with basically any other simple molecular covalent structure. They don't conduct electricity. Graphite is an exception. I'm not going to go into detail on graphite now because we'll go to it later, but graphite's the only exception in covalent bonding that can conduct electricity. So keep that in mind. Now let's move on to metallic. Metallic is a giant lattice, same with ionic, and it's bonding between metals of the same element. Keep that in mind. 2 metals, same element. It has to be the same element. How this bonds is because of electrons being delocalized. Between these metal atoms, they're going to have a sea of delocalized electrons. They love using the word sea of delocalized electrons. That's something to point out. Sea of delocalized electrons. And they have these ions of metal atoms. So they have lost like outer shell electrons. That's why they have these electrons kind of floating around and being bonded together because they form ions. These electrons on the outer shell are all just kind of moving around. So the arrangement essentially is a lattice, and then these electrons kind of just moving through the structures, these sea of delocalized electrons. They have a very high melting point because the metallic bonds and the electrostatic attractions, there are a lot of them. Therefore, it's very high melting point. Because they have these sea of delocalized electrons just moving around the structure and they carry charge, as I've said, anything that carries charge conducts electricity. So it's going to conduct electricity when it's solid because they have these delocalized electrons just floating around the structure. One thing to note about metallic bonding, they're malleable. So yeah, they can move around a bit. This question, the Buckminster Fullerene molecule, I think this is only in triple sciences, but yeah, maybe not, or it's in higher for sure. The Buckminster Fullerene, you need to know the shape of it. It's like a sphere, and you need to know the functions of fullerene. So just to give you the answer right here, Buckminster Fullerene will give you like it's spherical, and you need to figure out what fullerene does. So you need to memorize some of these functions. Now I want to talk about graphite. You guys can look at this question yourselves back home. I just want to like talk about the Buckminster Fullerene thing because that's just stuff you need to know. Right, the structure of graphite. The structure of graphite is really interesting. It is covalently bonded. So the carbon is bonded to 3 other carbons. So it's covalent bond and it's a giant structure. And they're sheets. So they're sheets of graphite. Between these sheets of graphite are weak intermolecular forces. This is important to note. Between the sheets are weak intermolecular forces. Because they have weak intermolecular forces and they're sheets, they're layers of graphite, they can slide over each other. The key word really is just sliding over each other. These sheets can slide over each other. And because they can slide over each other, that makes them soft and slippery. So that's kind of the first part I want to talk about. Well, it's the second part. The first part is they're giant covalent structures, 1 carbon bonded to 3. And the second part I want to talk about, layers of graphite, weak intermolecular forces between them, they can slide over each other, making them slippery. Third part is them being a good electrical conductor. Graphite can conduct electricity because of its, honestly, it's just an exception of its structure. They have electrons moving around this structure as well. They have electrons floating around and moving around this graphite structure. And as I said, anything that carries charge can conduct electricity. So because of these electrons just floating delocalized around the structure, it is a good electrical conductor. So in this question, it's asking why graphite is a good electrical conductor and why it's soft and slippery. Talking about bonding, here is the answer. Covalent, giant structure, 3 bonds, 3 covalent bonds, 1 carbon, 3 different carbons. They have electrons delocalized, therefore they carry charge and they can conduct electricity. They're layered and they have intermolecular forces that are weak between the layers, so they can slide over each other and therefore they're soft and slippery. This is always a 6 marker that shows up every year, so please know this all. Please know the graphite structure well. But that's all I want to talk about graphite. Okay, I hope everyone has had a good lunch break. Don't want to waste any more time, so we're just going to get straight back into chemistry. Yeah, hopefully everyone has been recharged for that break. Okay. Okay, next topic we're going to be talking about is making salts. And this thing, there are a lot of processes we need to look at. So reactions with metal hydroxides and acids, metal oxides and acids, and metal carbonates and acids. So the basics of neutralization is basically reacting hydrogen ions with hydroxide ions to form water. So if you're a neutralizing acid, you're trying to use up all of the hydrogen ions. If you're neutralizing a base, so an alkali, you're trying to get rid of all of the OH minus ions. So you can see from this equation, it's going to be hydrogen ions plus hydroxide ions giving you water. And that is the equation right there, H plus OH minus gives you H2O. Acids are neutralized by alkalis generally and bases, and this gives you salts and water. And that's like kind of the general equation that you're going to be getting. I want to emphasize this as well. If you are writing equations for neutralization reactions, the ionic equation is always going to be H plus OH minus gives you H2O. If it's a neutralization reaction, there is no other ionic equation. So that just makes it simpler for you to understand. So let's look into the 3 things that you can get, 3 different types of equations. First thing, it is the metal hydroxides and the acids. If you react a metal hydroxide with an acid, you're going to get a metal salt and water. That's the same thing with metal oxides. If you react it with acid, you're going to get a metal salt and water. And the only difference is that metal oxides, sometimes you do need to heat it up for the reaction to take place. But generally, the reactions will always give you a salt and is always going to give you water. Again, I say this, neutralization reactions always will give you an ionic equation of H plus OH minus gives you H2O, as you can see here. Now let's look at the neutralization with metal carbonates to produce salts. When a metal carbonate reacts with acid, you do get metal salt and you do get water. However, you also get an extra thing, which is carbon dioxide, is in the equation. A lot of the times in your exam, you're going to be getting these 3 different scenarios where they give you an acid, so usually hydrochloric acid like HCl, and they'll give you a metal hydroxide, a metal oxide, or a metal carbonate, and you have to figure out the equation. So just be wary of what you will get. If you have trouble deducing it, at least you can write water in one of your equations, and if it's a carbonate, at least you can write carbon dioxide in your equation to get some marks. And within this topic, you also have practical of soluble salts. So how soluble salts are made, essentially, they can be made from acids. And as I said, you can react them with any soluble, insoluble substance, metals, metal oxides, metal hydroxides, or carbonates. Now, the diagram on the right shows you the practical that you need to know extremely well, step by step, why you do each step, so that you'll be able to answer some of the questions you'll get in the exam. Because with this practical, it's producing soluble salts. This is what the practical is about. You need to be able to know what's happening in each step, and you need to be able to understand why. So I'm going to go through this slowly with you. First part, when you're producing a soluble salt, you have the acid, and you're going to add the solid into the acid and mix it until there are no more that reacts, basically until there is excess solid. When the solution is saturated, filled with the solid, adding more of the solid is not going to dissolve any further. That's when this solution is saturated. The reason you want to do this is you want to make sure that all of the acid in the solution has reacted. That's the reason you want to have this excess. You want to mix it and react it until it has excess solid. You want to make sure all of the acid has reacted. The second step, you're going to heat this solution until it evaporates a little. The reason you want to heat the solution is because you want the process, the reaction to go quicker. You want to give it more kinetic energy. You want it to react a lot faster. That's the reason for step 2. Step 3, you're going to filter to remove any excess solid and leave the solution of the salt in some kind of evaporating dish. That's where you're going to get your salts. But the reason you're going to filter it is so you can get rid of any of the excess solids that you've left in there. In a question, if it asks you why you want to filter it, you have to name the specific solid as well. I want to emphasize that. Final step, you don't need to really know the reasoning behind it. It's just you have the evaporating dish, you let it crystallize, and you're going to get your metal salts. You're going to get your crystals. And usually to evaporate any of the solution, you're going to either use a water bath or you're going to use an electric heater. Those two things. One of the two answers will be correct, so don't worry about that. I'm going to repeat myself again, explaining this experiment, because this is important. You're going to add the solid into the solution, into the acid, until no more solid reacts, until it's in excess. This is to make sure the acid fully reacts. Second step, heating it up until some evaporates. This is to make sure the reaction goes faster. This allows to have more kinetic energy and therefore it goes faster. Third step, filtering. Filtering any excess solid, making sure that there's not any little bits into the solution that you put into your evaporating dish. Fourth step is just waiting it to crystallize, and you evaporate this using a water bath or an electric heater. Those two things. I hope that was clear for everyone. So we're going to move on to a question. I'm going to just explain this because these are 1-mark questions. First question there, the potassium, telling you the neutralization of hydrochloric acid and potassium hydroxide. To be able to figure this out, usually I would write an equation. So you can just write out HCl plus KOH and you can figure it out. Because you know that neutralization, you're going to have a salt and water. So by taking out the OH from the hydroxide, taking the H from the acid, you're left with Cl and potassium. So that would just tell you that the salt is potassium chloride. That's the way you would think about it. That's the way you would process how you figure out what the salt is through the neutralization. Removing the H from the acid and removing the OH from the hydroxide. Whatever is left, that's going to be your salt. Second question, write an ionic equation for the neutralization of hydrochloric acid with potassium hydroxide. And I already emphasized this so much earlier. The ionic equation for neutralization will always, always, always be H plus OH minus gives you H2O. There's nothing around it. So those are the kind of the questions I wanted to look at. This question on the left and on the right, this whole page, the slide that you're seeing right now, is emphasis on the practical I just showed you. So it's asking you, give the reasons for these few steps in this experiment. Step 2, warming the sulfuric acid. Let the reaction go faster, as I've said earlier. So this is all just like repeat of what I said. Speed up the reaction. Step 5, repeat steps 3 and 4 until there's magnesium oxide remaining in the beaker, until there's excess solid in the beaker. Why are we doing this? To make sure all the acid has reacted. Step 6, why are you doing step 6? Why are we filtering the mixture? To remove any excess. And I've said before, if you're doing this in an actual exam paper, you have to specify what solid they are telling you. So instead of saying to filter the solids, you have to say remove and filter the excess. In this case, magnesium, I think was the thing, like magnesium oxide. Remove any excess of magnesium oxide. That is the solid you have to write to make sure you get the full marks. Final part, how should the filtrate be evaporated gently in step 7? Again, I mentioned earlier, there's only 2 things you would evaporate it with, either a water bath or an electric heater. So any of these 2 would be completely fine. So that would be the mark scheme for this question. So now I want you guys to actually try. Okay, so this is not in triple science, I believe. No, sorry, this is not in combined sciences. I think this is only in triple sciences when it comes to mole calculations. So if you are in combined sciences, I guess have like a 2-minute break. If you are in triple sciences, can you guys please attempt to do this question because it's quite hard, I would say. Sorry, my bad. I think combined sciences, you need to do this as well. I'm just realizing it's only concentration that you don't need to do. So attempt this question, please. Okay, I don't want to, let's just move on to the questions. Right, here is asking you first to calculate the number of moles of iron used, right? So you have iron here. It tells you have 14 grams of iron. And in the 14 grams of iron, you also know that the relative atomic mass is 56. So the first thing I'm going to figure out is the number of moles of iron, right? And using the equation, moles equals, sorry, this is really hard to do, mass over mR. That is horrible. Right, maybe I should type this up. That's going to give you 14 divided by 56. That's going to give you the moles. And that's going to give you the moles of 0.25. That's iron. So that's the first step. Second step is asking you to figure out the number of moles of chlorine that react with the 14 grams of iron. Because we need to figure out the moles of chlorine, we need to look at the number in front here, the 3 and the 2. The moles to mole ratio here is 2 to 3. So instantly, I need to figure out what the moles are by doing dividing or timesing. So from that, I'm going to know that 0.25 divided by 2 times by 3 is going to give you 0.375 moles. That will be the moles of chlorine. Finally, now that I have the moles of chlorine, I need to figure out the volume that I need. I have been told that the volume of 1 mole of gas is 24. So to figure out the moles of chlorine, which is 0.375, I'm just going to do 0.375 times 24, which should give you 9. Ooh. It's not. This should give you the answer of 9. That's not. There we go. So the answer will be 9 decimeters. Any questions regarding this? I know I saw a few questions, like, is there any questions regarding the this question? This is a toughie. Seems like we're all okay. Okay. That is the mold questions. This one is just an example. There can be harder ones, especially for triple sciences. So everyone who is in triple sciences, and I mean even in combined science as well, please be careful of like these mole calculation questions and do as much practice as you can with this. Okay, now we can. Okay. All right. Moving on, now let's talk about the reactivity series. Okay, the reactivity series, what essentially is, it tells you when metals react with other substances, they form positive ions. And the reactivity is related to the tendency it forms the positive ions, how easily it can form these ions. So the more reactive the metal, a more reactive the metal, the more you can displace the less reactive metals. So if it's higher on the reactivity list, it's going to be able to displace those that are lower on the reactivity list. For example, zinc and iron oxide, is higher on the reactivity list compared to iron. So zinc can displace iron to form zinc oxide, and you can extract iron. So sometimes when they're asking you questions on, oh, there's something you need to extract this specific, you need to extract this metal. How would you able to do it? If I want to extract like copper, I can use just a more reactive metal and just displace it to just take the actual copper itself. So that's how the reactivity series kind of works. For triple sciences, you have to memorize the order of the reactivity series. And I emphasize this because later, when we move on to talk about electrolysis, you need to know the details of it. So you need to memorize the reactivity series well. Use, I think, a mnemonic. Usually there is one. Now I'm just going to talk about the reactions that are involved. First, let's talk about the reaction with oxygen. The higher the reactivity it is on the reactivity series, is obviously going to be more reactive. If it is really high on the reactivity series, it's going to burn with oxygen to form an oxide. If it's below carbon, it's going to form oxides when heated, but it burns if it's a powder. If it's copper, it's going to form an oxide when heated, and there's not going to be any reaction for silver, gold, or platinum. Silver, gold, and platinum, these three metals, they have no reaction for anything. Absolutely none of these. They're just so unreactive that they don't react with anything. At least not with any of these on the list. Reaction with water, anything below carbon, not going to give a reaction. Everything above carbon is going to react with this water, and it's going to give off a hydrogen gas. The test for this is using a, I think, glowing splint or burning splint, I believe, by putting this in, and then it's going to give a squeaky pop sound. I believe that is the test for hydrogen gas. Reactions with acids, anything below hydrogen, not going to react. So even copper is not going to react in this case. Zinc and iron, it's going to react slowly and give up a hydrogen gas. And as it goes higher up on the reactivity series, it's going to react even more and more vigorously. All of it's going to release hydrogen gas, but it's just going to be react more vigorously when you get higher on the reactivity series. So that is the reactivity series on its own. There is a question, again, on plan and investigation. And if you remember in biology, when I explained planning and investigation, how you would do this, it's just describing the experiment, control variables, results. This works exactly the same with this question. So I'm not going to break down this question too much. I'm just going to tell you that this is the form of it. So it's telling you to plan an investigation, find the order of reactivity with 3 unknown metals, and you can figure it out using the temperature change. So describe the experiment. Let's start with one metal. You're going to put this metal, put it reacted with with some acid. It says here hydrochloric acid, reacted, mix it, put it in a polystyrene cup, figure out the temperature change. As you're describing the experiment. There's definitely more details than what I just said, but it's just describing that experiment. Control variables, same volume of hydrochloric acid, same volume of, same concentration, same pH, same state of metal. So powder, solid, same volume of metal that you're using. All of these control variables, just start naming them and naming them. That will already give you marks. Final section of it, results. So how would you be able to deduce these results? You do this with the 3 metals, you repeat it. Then you figure out which one is higher in the reactivity series by figuring out which one has the higher temperature change. If it changes the most, then that's going to be the most reactive. So that's just kind of how you would break down this question. So you can see here, talks about describing the experiment, control variables, or like repeat to make it more accurate, and then results. That's literally that's kind of the structure of planning and investigation, and it works across all sciences. So if you see plan and investigation, just think of those 3 steps. That was the way I would go at it. That is kind of it for reactivity series. Titrations, this is mainly for triple. I think there is a little bit for combined sciences that they need to know a bit about it, but it's mainly for triple. So I'm just going to talk about titrations. If you plan on doing A-level chemistry, you're going to do titrations a lot. So I'm just going to break it down for you. What a titration essentially is you're trying to figure out a concentration of an unknown, you're trying to figure out the concentration of a solution by reacting it with a different solution of a known concentration. So let's say I have this hydrochloric acid. I know this concentration is 0.1 moles per decimeter cube. I'm going to use this to figure out the concentration of this alkali, and by reacting with it. That's what titration is. So usually it's going to be an acid and alkali neutralization action. The reacting volumes of acid and alkali can be measured by titration using a suitable indicator. So I think the ones that you guys know the most is phenolphthalein and methyl orange. Methyl orange turns from orange to pink, and phenolphthalein goes from colorless to pink. Do never, never, never write the word clear. Clear is an incorrect answer. Always say the word colorless. All solutions are technically clear. You can see through them. That's what clear means. If you want to say something that's like transparent, like there's no color, colorless, use the word colorless to clear. It's colorless to pink. Never use the word clear when you're talking about indicators. Okay. A few things you need to talk about in titrations. What kind of burettes, pipettes, like what kind of things you need to use. So you need to use a pipette, you need to use a burette, and you need to use a conical flask. Those 3 things. And the pipette is filled with a pipette filter. Okay, now I'm going to break down the steps of what you need to do. First, put a known volume of the solution of this acid or alkali, whatever you're using, and measure it out using a pipette and put it into a conical flask. This is the solution that you don't know the concentration of, but you need to have a fixed volume. This is very important for titration calculations. Then add a few drops of indicator, a few drops, never like a whole bottle, just a few, maybe 2 to 3 drops. The other unknown concentration of acid and alkali is then added to the conical flask using a burette. So essentially, the thing that you know the concentration of, you're going to put into the burette, or it can be the opposite. So I told you that the unknown concentration will be in the conical flask and the known one is going to be in the burette. That also works. You can also do the opposite. Both work exactly the same. Then you're going to keep adding drops of these acids or alkali into your solution until it reaches the endpoint. And the endpoint is when the color change is seen. When there is, when it goes from colorless to pink, or it goes from orange to pink, depending on which indicator you use. Then you figure the volume that is added from looking at the burette at eye level. And you're going to keep repeating this until you have concordant results. Concordant results meaning it's only 0.5 centimeters cubed apart. So 23.5 and 24, concordant results. That is concordant results. And you can only use that and figure out the mean volume through that. I think that is it for titrations of understanding it. There are calculations with titrations. Again, I think this is also mainly in triple that you need to know. Moles is equal to the concentration times volume. And you have a lot of these titration questions, and they show up in every single chemistry triple science exam, every single one. And it's always one of the harder questions. So if you want to try and get as many marks as you can, do as many titration calculations as you can, because that will help you figure out how to answer these questions. There is a question on the titration. I'm not going to go through this with you. I can if you guys want me to at the end of the chemistry session, because some of you might struggle with titration questions. But I'm going to move on because there is a lot to go through in chemistry. Okay, electrolysis. Before I move on, any questions so far? Is anyone confused on anything that I've said so far? Any questions on the previous topics I've talked about? You're welcome to put it in the chat. Okay, seems like we're all good. We're now going to move on to electrolysis because that is quite the big topic. So, electrolysis with combined sciences, you need to know just molten. You don't need to know what happens in aqueous. Triple science you do, so let's break that down. In combined sciences, first of all, and I guess just both sciences, electrolysis, you need to know what it does. It's basically decomposing the ionic compound using electricity. So if you have NaCl, for example, that ionic compound is going to decompose. It's going to go Na ions, and then Cl ions. And they split this up using electricity. The cathode, the positive electrode, the negative electrode, and it gains positive ions. So essentially, the cathode is the negative electrode. Positive ions are going to go to this negative electrode because positive goes to negative, and is going to gain electrons. These are called reductions. At the anode, negative ions are going to go to the anode, the positive electrode, and it's going to lose electrons. This is oxidation. I know this is confusing. Use a mnemonic oil rig. Oxidation is loss, reduction is gain. So oxidation is loss of electrons, reduction is gain of electrons. And negative ions are losing electrons to form these compounds, and then positive ions are gaining electrons to form these compounds. So if I have a bunch of Na that's going all the way to the cathode, it's going to gain electrons to form sodium. Same with chloride ions. It's going to go to the anode. It's going to react together, form chlorine as it loses electrons. The half equations are usually represented. Triple sciences, they heavily ask you on writing half equations. You combine sciences too, but more on triple. Yeah, that is kind of the gist of it. With molten compounds, it's very simple because molten compounds, there's only two ions in it. It's just going to be the sodium and it's just going to be the chloride. I'm just using sodium chloride as an example, but it's just going to be the two ions you have in there, the positive and negative ion. So if you have a molten ionic compound in electrolysis, you're just going to produce those two things. The metal is going to be at the cathode. The non-metal is going to be at the anode. It's simple as that. Nothing more to explain. That's all combined sciences kind of need to know regarding electrolysis. I know there's a few little extra details, but that's kind of the basics of it. For triple sciences, this is where this is very, very difficult because it talks about aqueous solutions. Reason it's so complicated is because aqueous solutions, not only does it have the positive and negative ion, it also has water, meaning it also has OH minus and H plus in it. So let's break it down on what would happen. Okay, this is why you need to understand the reactivity series. At the cathode, where the metal is usually produced, if the metal is more reactive than hydrogen, so the H in this case, if the metal is more reactive than the hydrogen will be produced instead, not the metal. So let me say that again. At the negative electrode, in aqueous solutions, when there are both positive and negative ions from the ionic compound, you still have H plus and OH from the water from the aqueous solution. Because the metal is more reactive than the hydrogen, the H pluses are going to react and they're going to form H2 instead of the metal. So anything that is below hydrogen in the reactivity series is going to produce the metal. Anything above is just going to produce hydrogen. Okay, now for the anode. The anode, because of OH, the oxygen is going to be produced on the anode unless it's a halide ion. So group 7 ions. Chloride, fluoride, bromide. If those are in the solution, instead of oxygen, it's going to produce that gas, chlorine, fluorine, and bromine. I'm hoping that makes sense. It is a bit complicated with aqueous solutions of electrolysis, but that is kind of the gist of it. So I'm going to reiterate again, with molten compounds, this is combined sciences and triple, molten compounds, it's just simple ionic compounds. So the positive goes to the positive is going to form the metal, negative ions form the non-metal, and that's it. That's the only things you're ever going to form. There's no other thing that could form because there's only those ions in the molten compound. In aqueous solutions, because water breaks down to H and OH minus, you're going to have different things. For the metal, if it's more reactive than hydrogen will be produced. In the non-metal, oxygen will be produced unless it is halide ions. So anything in group 7. I hope that explained that more clear. Okay, within electrolysis, there's also an extra thing you need to know, which is hydrogen fuel cells. This includes both combined and triple. However, combined, the things you need to know is slightly different. I'll just talk about what you need to know for both. So generally, these hydrogen fuel cells, they're supplied by an external source of fuel, and oxygen and air. So it's like hydrogen, and then just the oxygen in the air, in the atmosphere. The fuels oxidize electrochemically within the fuel cell to produce a potential difference. So this produces a voltage. And usually what happens is the hydrogen reacts with the oxygen to produce water, and any excess fuel is going to be reused. And this is a really good alternative to rechargeable cells and batteries because it's very efficient and it only releases water. However, it's very, very expensive. And the reason a lot of us have not been using these hydrogen fuel cells because hydrogen gas is so extremely flammable. So it can be very dangerous and very difficult to store. So the main difference between combined and triple, I just wanted to talk about this first, is that the notes, what you need to understand. Electrolysis, you guys focus more on half equations, reactivity. And for hydrogen fuel cells, you only need to know the simple word equations and compare traditional batteries to hydrogen fuel cells. However, if you are doing triple, you need more detail on basically everything, and your comparison to hydrogen fuel cells are comparing them to normal rechargeable cells. Just wanted to talk about that a little bit. But the general understanding is that fuel cells, they are a good alternative for rechargeable cells, but they're kind of hard to use right now because they're expensive and they're very, very flammable. So yeah, but electrolysis should be done on both combined and triple, but electrolysis, you don't need to know as much. I'm hoping that is clear in the differences. That is it for electrolysis. This was a very hefty topic. Any questions regarding this topic? Because it is quite difficult. Okay, if there are no questions, I'm going to move on. But again, there is a Q&A box that you can feel free to text it. These are a few questions. I do want to have a go at doing some of these. So let's talk through here. 6.4. It tells you that an aqueous sodium chloride solution is electrolyzed in a different industrial process. Two gases and an alkaline solution are produced. So it tells you asking you which two ions are present in the aqueous sodium chloride solution in addition to sodium and chlorine ions, chloride ions. So when it comes to this question, someone asked a question, I'll answer that later. But the two ions are present in the aqueous solutions in addition. So it's asking you what ions are in the solution except for sodium and chloride. So it tells you there, right? It tells you in the question it's an aqueous sodium chloride solution. So you know that there's going to be sodium chloride, so sodium and chloride ions, and there's going to be other ions in there. Because there's water, it's going to be OH and H+. So the OH and H+ are going to be the other ions present. Now it's asking you for the alkali solution produced. This is where we need to think about it more deeply. This links to the next question, actually, asking you why that alkali solution is produced. So I'll explain that. Within electrolysis and aqueous, again, as I've said, if it's more reactive than hydrogen, hydrogen's going to be produced. And if it's a halide ion, halide ions are going to be produced. If that's not the case, oxygen will be produced. In this case, sodium is more reactive than hydrogen. So sodium is not going to be formed, but instead hydrogen. So now we only have sodium ions left in the solution. Now it looks on the other side. Chloride ions are going to be produced because chlorine, that is a halide. Therefore, we're going to produce chlorine. Then we only have OH left. Now that we have only sodium and OH left, add them together, they're going to react, and that's going to produce sodium hydroxide. So hopefully that that's clear. Hopefully that explanation is clear. I know there are a few questions on here. Okay. How do you know whether it is molten or aqueous electrolysis? It does tell you. It does tell you in the question. I highly doubt it they will ask you to figure that on your own. It will tell you in the question, so don't worry about that. Okay. Any questions regarding electrolysis? We're going to move on to the next topic, but that's kind of it for electrolysis I would like to talk about. Doesn't seem like it. Okay, we're going to move on to... Okay. Wait, there are other questions. Okay. So, rate of reaction. Let's talk about this as well. Rate of reaction changes during a reaction. So when you're reacting something, there is going to be a graph and this, like the slope, as you can see in the right side of this slide, this diagram. Most reactions are really, really fast in the start. So that's when the slope is the steepest. And over time, because reactants are getting used up, the reactants are reacting. They're going to slow down, slow down, slow down until it plateaus. It plateaus because there's no more reactants. Everything's reactant. It's over. That's it. So in a rate of reaction graph, you'll see that it's very, very steep in the beginning. In the initial rate of reaction, slows down and then plateaus. That's always going to be what it looks like. As the rate changes, we can measure the mean rate over time, and this is used by figuring out a tangent. The mean rate of reaction is just reactants used up or products formed. when you're reacting to something, you're going to use up all of your reactants or you're going to form a certain product. So to figure out the rate of reaction is just the products formed divided by time or reactants used up divided by time. So the units are usually grams per second, cm cubed per second, or mole per second. It really depends on what exactly is the reactant or product that you're measuring. So if it's like a mass, it's in grams. If it's volume, it's going to be centimeters cubed. But it's always going to be per second. The second is the standard unit you'll be using when you're measuring a rate of reaction. So as you see on the rate of reaction graph, you can draw a tangent to figure out the rate of reaction, because the slope, basically the gradient of the point is the rate of reaction. And the way you figure out rate of reaction is change in y over change in x. And this is the typical, this is just the math equation essentially. It's just change in y over change in x. And sometimes they will ask you to figure out the rate of reaction at a certain point. So at maybe like 20 seconds, figure out the rate of reaction. So at the point from 20 seconds, you draw a straight line, draw a triangle, and then figure out the rate of reaction just from that triangle. Change in y over change in x. The thing with rate of reaction, we have the collision theory, and the reason why anything reacts is because of your particles and these particles colliding with each other. It's very important that you understand that rate of reaction is because of these particles colliding and frequently colliding with the wall or colliding with each other. So the collision theory is essentially saying that the rate of reaction occurs from the successful collisions when reacting particles collide with each other and with sufficient energy. So it's how often they collide with each other and how much energy they collide with each other. And it has to be enough energy. The minimum amount of energy that the particles must have to react is called the activation energy. So anything below the activation energy is not going to react. This is why they talk about rate of reaction with particles. If the particles are not colliding with enough energy, it's not going to react. Increasing the concentration of reactants in solution is going to increase the frequency of collisions. Same thing with increasing pressure and same thing with increasing the surface area. To understand this, increasing the concentration means there's more particles, more easily collide with each other. Pressure, again, you're going to be hitting the wall more often, more collisions, more rate of reaction. Same thing with surface area, more collisions. All of it's just increasing the collisions. Increasing temperature also increases the frequency of collisions, but it also increases the energy. So this is the one thing that differs it from just increasing the concentration or the pressure. Those things increase just the number and the frequency of collisions. Increasing the temperature also increases the energy of collisions. This in turn also increases the rate of reaction. Catalysts, which is something that you do need to know, it's a big part of chemistry and also biology, but chemistry. Catalyst increases the rate of reaction by providing an alternate pathway for the reaction that has a lower activation energy. So it doesn't directly lower the activation energy. It finds an alternate pathway that has a lower activation energy, and this allows for an increase of rate of reaction. Important to note that catalysts never get used up. So if you add a catalyst into it, it's just going to decrease the activation energy, increase rate of reaction without ever actually being used up. And you can see the little diagram on the side. You can see that the activation energy is a lot lower with a catalyst. It's a lot smaller. So I hope that was understandable. This is a lot of math for rate of reaction. I'm going to skip through some of this because you don't need to know too much detail on that. So here, it talks about we're just going to quickly talk about this. It's saying that the student changed the investigation in the very beginning. It talks about collecting 20 centimeters of gas to make sure that the time was greater. So they wanted a lower rate of reaction because they wanted more time taken to collect this gas. So what would the changes be? If you want a lower rate of reaction, you're going to have to do the opposite of what I just basically told you. So essentially using a lower temperature, using a higher temperature is going to increase it. So you want a lower temperature to decrease the rate of reaction for the time to be longer. Catalyst is going to increase it, so that's wrong. Larger conical flask isn't going to do anything, that's wrong. Smaller pieces of zinc means larger surface area. So that's also going to be wrong. So your only answer left is going to be use sulfuric acid of a lower concentration. That is the answer for this specific question. The rate of reaction questions are very heavily application. So it's just understanding that higher rate of reaction, what are the factors? What factors affect this? And then you'll be able to apply it. The last question we've earlier just talked about, hydrogen gas. What's the test for it? Burning splint, squeaky pop sound. Very straightforward. I saw that there was a question in the chat. Okay. So I think that's that. Linking rate of reaction, there's equilibria. So this one, I find this one actually extremely, really difficult to explain because it's so hard. However, oh, by the way, if everyone has trouble with the slides, they're in the chat currently. So if you want to have a look at the slides, they're right there. So, equilibria, the reversible reactions. This is quite important to understand, so I'll try to explain this as much as I can, but this is a very hard thing to grasp. So don't worry, I'm going to slowly explain it. If you have any questions, ask. Okay. In a reversible reaction, so when something's at equilibrium, basically, A plus B goes to C plus C. Let's say that's the equation. In a reversible reaction, the reactants can form the products, and the products can form the reactants. I know that technically means that they're both reactants and they're both products, but the stuff in the front is the reactants. The stuff at the right side of it is going to be the products. And reactants can form the products can form the reactants. That's what's happening in a reversible reaction. When something is at equilibrium, it means that the rate of reaction is going to be the same forwards and is going to be the same backwards. So so this is kind of just the same rate of reaction forwards. The rate of reaction of the reactants forming the products is going to be the same as the rate of reactions forming the rate of reactions of the products forming the reactants. There's going to be the same forwards and backwards. That's when equilibrium is taking place. And mind you, when I'm talking about this, it means that it's taking place in a closed system. That means that the reactants and the products cannot escape. I know a lot of people are talking about asking for the slides. We will send them to you. We will send them to you even if you can't see them. We will figure this out at the very end of it. So anyway, yes. So, right. However, it's important to note that even at equilibrium, the direction of the reversible reactions can change according to the different conditions. And the conditions could be things like temperature, things like pressure, or concentration. And we will look through that through Le Chatelier's principle. Okay. So the Le Chatelier's principle and understanding equilibrium is that the conditions in a reversible reaction, whatever is forward is going to be the opposite backwards. If forward is endothermic, backwards is exothermic. I'm hoping that makes sense. Let's talk about Le Chatelier's principle, and let's talk about the three things: concentration, temperature, and pressure. A change in concentration, it will depend which direction your equilibrium is going to go at. So if I have more reactants, if the concentration of reactants increases, you're going to have more products because you're trying to balance it. Think of it like a balance. So you see the diagram in the bottom right? Think of it like a balance. If there's so much here, you want to balance it back by creating more here. So if a concentration of reactant increases, products are going to increase. If the concentration of a product decreases, if this goes down, more of this is going to react, so this will go back up. That's the understanding of concentration in equilibrium. So that's concentration. Temperature. Temperature, if it increases, it's going to go towards the endothermic direction. And if it decreases, it's going to go towards the exothermic direction. When you're given a question, either they will tell you which direction is exothermic and endothermic, or you have to figure it on your own by looking at the numbers. So they give you the reaction, and if the forward reaction, for example, is negative something joules, if it's negative, it's exothermic. If it's positive, endothermic. So if, let's say, the forward reaction is a positive number, like something joules, 56 joules. If the temperature increases, it's going to go towards the endothermic reaction, meaning it's going to go towards the forward reaction because the forward reaction is endothermic. I'm going to reword that. Again, that was very wordy. Temperature increases towards endothermic. Temperature decreases, goes towards exothermic. To figure out whether something is exo or endothermic, either they'll tell you in the question or they will give you the energy And the energy, if it's negative, it's exothermic. If it's positive, it's endothermic. So be careful with the question. That's temperature. Now for pressure. If the pressure increases, this is where it's a bit confusing, it's going to shift towards the side with the smaller number of molecules. So let me just type this out because it's kind of hard to explain just by that. Right. Let's say I have A plus B gives you, that's not actually equal, let's just pretend that's the reversible sign, 2C plus 3D. In this situation, in this situation, there are more moles on this side than on that side by looking at the number in front. There are 5 moles on this side, 2 moles on this side, because there's 1 and 1, 2 and 3. If there's an increase in pressure, it's going to shift towards the side with the less number of molecules, less number of moles. So if I increase the pressure, the equilibrium is going to go towards the A plus B side. If I decrease the pressure, it's going to go towards the side with more molecules, the 2C plus 3D side. I'm hoping that is clear. Oh, okay. So that is that. Okay. Any questions regarding that so far, or should we move on because there's more on equilibria? Okay. Doesn't seem like anyone has any questions. We'll move on. There are a few questions regarding equilibria. I do want to have a look at that. So I want everyone to just have a look at the I want everyone to have a look at this question. I'm going to give you guys maybe 30 seconds to look through it, and then we'll kind of walk through it. Have a look at all of these questions. Please have a look at all of them, please. Okay. To understand this, first of all, let's just look at the question. It's telling you that the equation is from 2NO2 and it goes to dinitrogen tetroxide, which is N2O4. The 4 reaction, it tells you it is exothermic. So it's asking you what's the color of the mixture when a new equilibrium reaction is reached. Sorry, I forgot to give you this extra information. It's asking you what happens when my bad, but it tells you, it's asking you, it increases the pressure in the gas syringe. So what happens when you increase the pressure in the gas syringe? What is the color of the mixture? Well, as I said, when you increase the pressure of the gas syringe, when you increase pressure just in general, it's going to move to the side with the less molecules. And because it's going to move to the side with the less molecules, it's going to go to the colorless side. So, therefore, the mixture is likely going to be a lighter shade of brown because it's going towards the colorless side. On that side, there's less molecules. Now let's look at number 9.5. What is the effect of increasing the pressure on the equilibrium position of this reaction? Again, with pressure, we're looking at the number of molecules in front. So on the left side, the reactant side, there's 2. On the right side, there's also 2 because H2 has one in front, I2 also has 1 in front. That means that increasing the pressure isn't going to do anything because they both have equal number of molecules on each side. So your answer would just be there's no effect because there's equal number of moles. Final question, effect of adding a catalyst. I have said that adding a catalyst does increase the rate of reaction. However, I never said it affected anything on equilibrium position. I told you that in an equilibrium and in a reversible reaction, rate of reaction is the same forwards and backwards. Therefore, adding a catalyst will not affect the equilibrium position. This is a bit of a cheeky question, and sometimes they do ask you this. So please make sure that you know that when you're talking about equilibrium and you're talking about increasing rate of reaction, if you do add a catalyst, rate of reaction might increase, but it increases both ways. Therefore, there is no effect on the equilibrium position. I'm hoping that is clear. Any more questions regarding this? Because we are going to be moving on from equilibrium to organic chem. Okay. Seems like we're fine. Okay. With organic chemistry, there are two parts to it. There's the okay. There's the addition polymerization, and then there's the condensation polymerization. With triple chemistry, I mean with combined chemistry, you don't need to know condensation, you just need to know addition. But with addition, we'll just talk about that first. What happens with addition and polymerization essentially is that, oh, okay, I see. Sorry, this is a different slide. Ignore the condensation polymers on the right side. We're going to ignore that. So first, we're going to talk about the reaction of alkenes. The functional group of alkenes is the C double C bond. Ignore everything on the right side. I'm so sorry about that. Alkenes, they burn in air. So they react with the oxygen in the air because they have incomplete combustion. So it's not completely combusted. Therefore, when alkenes burn in the air, there's some smoky flames. And it's very dangerous to have alkenes just laying around in this atmosphere, because if you have a lot of alkenes, it could cause an explosion. Alkenes can react with hydrogen, steam, and halogens through addition. And what I mean by this is that the C double C bond can break off and add on the things that it's reacting with. So let's say you have hydrogen. It's going to break the double CC bond and form an H on each side. Same with H2O. You have an OH and an H in H2O. The C double C bond is going to break, and you're going to link it with an H, and you're going to link it with an OH. So that's similar. If you're trying to do addition reactions, if alkenes ever react with hydrogen, steam, or halogens, it's going to cause an addition reaction, where this double bond breaks and forms a reaction with those C's. If it's H2, it's going to go to HH. If it's H2O, it's OH and H. If it's halogens, it's probably like something like Cl2. It's going to be C, Cl, C, Cl. That is just that for organic chemistry. There is a little bit of understanding of fractional distillation that you guys do need to know. This was not covered in today's seminar, but please go through and look at that as well. Now I want to talk about polymers. Sorry, that was a duplication of the slide, my bad. I'm sorry, this again. Yeah, triple science, you need to know condensation polymers. Combined sciences, you just need to know addition. Addition polymers is also using alkenes, where you're also breaking that double bond and then forming a bunch of just monomers added together, and very, very long link of these molecules added together. And this forms a polymer. So there are many, many small molecules, what we would call monomers. They join together to form this really large molecule, and that's what you call a polymer. Nothing else is formed in addition. You're just breaking off and reacting with the next. So you can see there in ethene, you're just breaking off the double bond and forming with another ethene. And you're just going to keep doing it. Nothing else is formed. Nothing extra is formed. It's just adding on. Condensation polymerization is slightly different. Condensation polymerization involves joining molecules with two functional groups, either from the OH in the COOH with NH2, or the two COOHs, or an OH. This is a bit confusing. We're going to go through it. In addition polymerization, you only have that one molecule. In condensation polymerization, you produce water alongside the polymer due to the condensation. So if you just look at the bottom diagram, you'll see there's a COOH and then OH group. So there's the two functional groups. The OH from the COOH is going to break off, and the H from the OH is also going to break off, forming water. By removing this water, they are going to form a bond of COOO. And that is what condensation polymerization happens, and that is going to be the bond that links them together. That is condensation polymerization. Usually it's COOH and OH or COOH and NH2. Depends on the situation. But the OH always breaks off from COOH and the H always breaks off from either OH or NH2. When you are trying to draw a polymer, be careful because when you're drawing a polymer, you have to draw it properly with the brackets and also, I'm gonna try to highlight this, but do you see this molecule right here on the side, this thing? You have to draw the brackets. You have to draw the little brackets on the side. The branches have to be sticking out of the brackets. And you have to write the N on the bottom corner. If you're trying to draw a polymer, if you don't draw the big brackets, you don't have the branches sticking out of the brackets, and you don't write the N on the bottom when you are writing a polymer, you're going to lose marks. So be super, super careful when you're drawing polymers. So I'm going to demonstrate this by writing a question. Right here. First of all, the first question is asking you to draw a circle around the functional group of this formula. You can see that's already an alkene just from the double-double bond. So the first thing I'm going to do is just circle the C-double-C bond. That's going to be the functional group. The main one I actually want to look at is the one on the right. It's asking you to complete the equation for the production of polychloroethene. So just from what I've said earlier, first thing to do, draw the N on the corner. Then to write this out, we're going to have C, big line, C, there. Then it has to be single bond because you've already broken it off to form the polymer. You draw the rest in. So in this case, it's just HCl. Right there. It's going to be H. Okay. We're not done. Now that I've drawn all this as well, remember you have to have this sticking out of the bracket. So you have to draw these bonds outside of the bracket. So draw exactly as it is, but as a single bond. Then draw the two lines, and then you're going to draw the N on the side. Remember, these are the things you have to draw. You have to get this to get all 3 marks. Do not risk losing marks just because you forget to draw the lines outside of the bracket or forgetting to draw the N on the side. Just remember that. Okay, this is great. Why does this keep... Okay, anyway, we'll figure that out later. But that is the main thing I want you guys to look at, which is drawing a polymer. So the answer here is going to show you here. So first of all, drawing the circle around the C-double-C bond. Then when you're drawing it, you should have a formula like this. Just drawing the same thing as the original monomer. And then N below halfway, so right there, 2 single bonds extending through the back brackets. So you have to extend it through the brackets. Okay, any questions regarding all of chemistry we've done so far? We're going to have about a 5-minute break, and then we're going to move on to physics, if no one has any questions. Okay, let's have a 5-minute break. And if you have any questions, go ahead and ask in the chat. But other than that, should be fine. Okay. Yeah, absolutely. I can go through the equilibrium shifts and effects of factors again. Yep, no problem. Hold on. Let me just switch to. Okay. Let me just. It is quite a difficult topic, so don't worry. Nope, not this. Okay. So, with equilibrium, there are three. Okay, can you specify a little more on what you want explaining? Do you want explaining on Le Chatelier's principle, where like if there's a change in concentration, pressure, and temperature, or do you want to understand more of like the reversible reaction stuff? Like, do you want to understand like the concentration, temperature, pressure change, or do you want the other stuff? I think it's probably more on the Le Chatelier's. Okay, okay. So, with Le Chatelier's principle, your equilibrium position is going to change depending on the condition. So equilibrium, let's say everything's going to be the same. It's going to shift depending on the condition. So let's say so if it's concentration, let's start with concentration. If there's a lot of concentration of reactants, I'm going to use the diagram of like the balance again. Think about like this is the balance. And I don't know if you can see my face, but this is the balance. If you have more reactants like this, it's going to be tipping over. To balance it back, you're going to increase the product produced. So if there's more concentration, more products will be formed. And if the product decreases, this is going to the product when there's less product, this is going to increase so that more product can be formed. So that's the balance. Increasing concentration, more product formed. I'm hoping that makes sense. That's concentration on that part. Temperature is a bit more straightforward. Temperature. If you increase the temperature, it will move towards endothermic side. If you decrease temperature, it will move towards exothermic side. And they will tell you in the question most of the time if it's exothermic or endothermic. So if it tells you the forward reaction is exothermic, and this person increased the temperature. If the forward reaction is exothermic, it means the reverse reaction is endothermic. Increasing the temperature goes towards endothermic side. So equilibrium shifts towards the endothermic side. I'm hoping that's clear with temperature. With pressure, if there's an increase in pressure, it's going to move towards the side with more molecules. So if you look at an equation and it says A plus B gives you 2C plus 3D, look at the numbers in front. A plus B is 1 and 1. A is 1, B is 1, so there's two molecules on that side. 2C plus 3D, there's 2 C's, 3 D's. So that's going to give you 5 molecules on the right. So 2 molecules and 5 molecules. If the pressure increases, it's going to move towards the side with the smaller numbers. So it's going to move towards A and B. If the pressure decreases, it's going to move towards the side with more molecules, the 5 molecules. So it's going to move towards C and D, 2C and 3D. That's pressure. Does that make sense? Is there anything you're confused about more specifically that you want me to explain? Or is that all good? I'm hoping that's all good.